It is the second part of section 5.2, regularization, bias-variance trade-off. Overfitting is a common problem in machine learning. If a model performs well on the training data but has lower accuracy on the test data, then it is most likely the sign of overfitting. Overfitting is due to high variance, particularly noise in the training data set. Look at this figure. Now, this point may be a noise. However, now the model is overfitted. In this case, if there is a point, new point comes here, then it can be classified as one of plus points, but it's well fitted, then the point will be classified as the circle point. And so overfitted model has low accuracy for the test data set. That's the sign of overfitting. Similarly, the model can also suffer from underfitting. In the case, the model is not complex enough to capture the geometric pattern in the training data set, so that later in test, also it shows very low accuracy. That is due to high bias, and that is related with also systematic error, so that the model cannot be complex enough. As in this figure, this is underfitted the model, so that it has error for data set, and also later on for the test data, it can have large error. And so we have to find a good compromise in model, so that we can get good generalization. Regularization is one way to find a good bias-variance trade-off. Also, by using regularization, we can handle some degree multiple local minima problem. And I'll explain later on what it means. The concept behind the regularization is to introduce additional information, which is a sort of a bias, to penalize extreme parameter weights. And the most common form of regularization is L2 regularization. Now, sometimes called L2 shrinkage or weight decay. Just simply, we are adding this term to the objective function. So we try to minimize this whole thing. Then also this portion will be minimized, which means that the weight, the W, will have lower values. So it is called now shrinkage or weight decay. Now, if you try to use this regularization, you have to be a little bit careful. Now, for example, here in one parameter case, okay, the optimal W, for example, for objective function, okay, it's given that way, and optimal W is here now. But if you are trying to add this term, then now that is quadratic, and now about 0, symmetric about 0, so that you are adding this quadratic function, and along with scaling lambda, then now in this case, the optimal solution will be far away from the desired solution. So you have to be careful. So here, W must be originally around 0, small. then you can use this additional term so that it'll be beneficial. And for example, once original object function is given around here, so that even is there are some local minimum, but it's given in this way, then by adding this quadratic term, if you choose a lambda large enough, then the addition will become here quite smooth, so that eventually local minimum may disappear. So this reason it can handle in some degree multiple local minima problem by adding this extra term. Okay. Regularization is another reason why feature scaling, such as standardization, is important. By scaling the data, we try to get the problem, get the object function, so that the optimal solution is around 0. It's small, and that's the logic behind the feature scaling. For regularization to work properly, we need to ensure that all our features are on comparable scales. Like this one, your data values are large in some portion and the other portion small, then weight will be the same way. The value have some large component, so that such regularization will make really big difference, so that optimization will not work well. Here, by choosing lambda, we can control the regularization strength. If you choose large lambda, then regularization strength is increased. If you choose small, then now is approaching the optimal value for the original the objective function. So that with good data standardization, you may start with relatively large lambda in the beginning, and then during the iteration, you may try to choose smaller lambda, and then eventually the computed W is the minimizer of original objective function. That's one strategy. We'll see later on some details in section 7.3. Thank you.